Hi, my name is Fred Pilon, and I'm presenting my final project for ECE 561. My project is titled An Embedded System for Position Control of a Mechanical Device for Acoustic Detection and Tracking. So the problem I'm trying to solve is that I wanted to use an embedded system to acquire and track an acoustic signature from something in the field, such as wildlife. So this is a prototype for a video tracking system, say, for field identification of said critters. I used a 4-microphone channel array and a pure tone from a smartphone to prove this concept out. So I used a ESP32 microcontroller. I used 4 microphones in a physical fixed array, and I used 2 hobby servo motors as a proxy for a 2-axis pointing device. The technical challenges I faced were 2 categories. So one was demodulation. So the first demodulator I tried out, I just software sampled 4 channels, one after the other in a round-robin fashion, and used FFT processing to try and tease out the phase differences between the 4 channels. So this system was good for bring up, but I found that the sampling rate was too low to use as a final product. The second demodulator I used was a I2S feature of the ESP32. So I2S is a protocol that's designed specifically for audio, so it was perfect for my application. So this was perfect for the sampling rate because you could program the sampling rate, and it used the system clock to ensure an accurate sampling rate, but it was too buggy in hardware and not fully implemented in firmware as yet also. So I moved to the next demodulator. I used a hardware phase discriminator, and what I did was I used an LM339 quad comparator to square up my sinusoids, and then an XOR chip to produce a PWM phase signal that I read into the ADCs of the ESP32. So this was extremely fast because it was done in hardware, but it was very noisy. The 5 volts 5-volt noise generated by this system was very noisy, a lot of switching noise. So the next modulator I explored was microphones sampled in pairs so that I got twice the sample rate of demodulator 1. And then I derived phase differences from the FFT, the phase portion of the FFT. So this was flexible in the frequency domain, but still too noisy. Measuring the phase of a phasing noise measurement of a noisy system was just too noisy for my use. So I moved on to demodulator number 5. So demodulator number 5, microphones were sampled in pairs again to get the double sample rate. And then I used a time domain phase discriminator to demodulate the phase. So this is what I used for my final project demodulator. I added an integrator for noise immunity. And the last thing I would have wanted to have added was code support for flexible frequency discrimination, but I just got it just working for a single frequency, and future expansion I can move to other frequencies or a broader band. So another technical challenge I had with this was, as I've mentioned already, is noise. So these servo motors are very noisy during operation. I added a large electrolytic cap across the 5-volt rail, and that helped. The integrator helped a lot, and I implemented a PES spike elimination at the end, which worked very well, and I got everything working just fine. So here's the approach I used to solve this problem. So here's a simulated system. Let me grab a laser pointer here. So here's 2 simulated. This is just one phase channel. So I've got 2 microphone inputs. And as I said, this is simulated, but I added some noise too. So this simulates the real microphone. And you can also see that it's from +1 to -1. And that's what I did in the software as well. I normalized all the signals so that what we are going to do is we're going to detect detect zero crossings to determine phase. And so here is that same signal, that same simulated noisy signal, and I've filled in at the black dots here are the zero crossings of these the positive zero crossings of these sinusoids. And from that zero crossing, we can determine phase one to the next. And so the way I determined the zero crossing was I took the value that was the first sample below zero and the first sample above zero and did a linear interpolation and determined that point where the zero cross is. And so the phase is just the difference in these 2 points. And so you can see here that the phase is, input was 25 degrees and I got about 25 degrees out for the determination of the phase. And so there's another case where if the phase is such that channel 1, the blue channel here, its first zero cross doesn't come until after the first zero cross of channel 2, then it looks like, so the phase is the difference between these first samples, and so it looks much bigger than it is. We really want this 45 degrees here, but what we're getting is this big phase shift here. And so that was a simple code path to determine that. So I calculated that it was 314.5 degrees, and so that's out of the physical realm of possibility for the acoustic array that I have set up. So if the phase shift is over a certain amount, I subtract 360 to get the real 45 degree phase shift. And yeah, there I point that out. And so here is a couple of traces from real data from my system. The blue is channel 1. So now there's 4 microphone inputs are distilled into 2 phase channels. So blue is 1 and green is 2. And here is the phase so I did an experiment where I moved the source through different areas of the array and captured the data through MATLAB. And you can see the dotted lines here are the integrator that I mentioned above that I implemented. So you can see the integrator starts out not caught up to the signal, but it does catch up to the signal. And you can see too that it's got a little phase delay between the commanded and the integrated position, but that is so small it just doesn't matter for our purposes here. So the integrated value is the value that we sent out to the servo motors. And so another interesting thing that we can do with this data is we can plot integrator. So here what I've plotted is I've got a trajectory of the I've called this the source trace path, or a trajectory plot. So I plotted integrator 1 versus integrator 2. So this gives a spatial representation of where the acoustic source was. The information that's missing from this is time. There's not a time piece to this. So in MATLAB, I wrote a routine that plots each point in turn so that we can get an idea of what this trajectory looked like in time. So let me get rid of the laser pointer and do this so you can see. We'll see now. So here I'm in MATLAB and I'll implement the routine. So there you can see the trajectory is going. There you go. And then now I'm moving the smartphone in a circular manner, and it's about to end there. So we can see in time what happened with the trace of the path that I took. And so there's several ideas I had for the future work on this project. So a few hardware ideas. One of them was just add more microcontrollers. They're really cheap. Another one is add more microphones. They're also really cheap. We could lay out a PCB to mitigate some of the noise problems that I had. Get a much smoother system. I had several code ideas. I would really like to get back to that I2S feature that exists in this hardware. because it just seems like such a cool way to go. And I'd like to implement beamforming, so cool signal processing techniques that would make use of the speed of the I2S system to do narrower detection of the acoustic source. And I think it would be a really fun thing to implement a communication system amongst these microcontrollers. You could implement partial arrays on separate microcontrollers and then use the GPIOs to communicate amongst the different processing units. I think that would be a fun code project. And that's my project. Thanks for listening.